All right, so I'm gonna do my best here. I forgot my tablet at school, so I'm gonna do my best with just holding my iPad here and trying to show you what's going on. We're almost done with this. I'm on page 357 right now, and we talked about yesterday the sigma notation, and we didn't quite finish, and so we're looking at how to generate Riemann sums using sigma notation. So I'm gonna, it's all right here, but I think it gets a little confusing when you get caught up in, like how are they wording all of this stuff here. So I've made a little picture. I'm gonna talk about this definition down here. And I'm gonna re-say this in a second, but remember what we're doing with Riemann sums, and that is finding areas of rectangles and adding them up. The reason we're going to sigma notation is because we need a more efficient way to generate all of these areas and add them up compared to just hand doing it all the time. And that's the only difference of what we're doing is how does this sigma notation look like? What is it doing to generate these areas? Okay, and so this left Riemann sum, the x sub k star, they give you this formula, and that's really where it gets a little confusing. So I drew out a couple pictures here, but the first thing I want to point out is back to this before I look at the other pictures. What we're talking about here, right here, is an area of a rectangle. This is the width along the x-axis, and this is the height, right? So that's the x value that we plug into our function in order to get the y value of that rectangle. And we're doing this for n rectangles. Starting at the first rectangle, we're going to the nth rectangle. And so then what does that look like in notation? What is the sigma notation doing? So it's taking the first, right, it's starting at k equals 1, and it's, let me get my pencil here, right, it's starting at k equals 1, and so then we're finding the area of the first rectangle. This change in x is always going to be the same. Remember, we take our endpoints of our interval that we're looking at, b minus a, and divide it by however many subgroups we're doing. Okay, so that's always going to be your width. We have decided to create the width the same every time. The only thing that's going to change is the y value. So then we're saying, okay, this x value is coming from the first rectangle. And then I'm plugging it in, finding an area. The next rectangle, it's the same width, but I'm getting the height from the second rectangle. That's what this little 2 is saying. The second rectangle, I'm picking some x value. That's the star, some x value in this second rectangle, plugging it in to get our y value so that I can find an area of the second rectangle. And then the third rectangle and so on. And so that's what's going on with this notation here. And so then if you look back at page 357, they have left, right, and midpoint. And the only thing that's different, and I'm kind of, see if I can do this here. I apologize. The only thing that's different is how is the x value getting generated. I'll do it with one hand here. Okay, so they're all going to be basically the same. And remember what we're trying to do here with this notation is come up with the y value, because our x value is going to be this length, this length, which is going to be equal to this, which is going to be equal to this. So this is a left Riemann sum. And again, what does that mean? Well, our grid points are going from a to x sub 1, then x sub 1 to x sub 2, x sub 2 to b. These are all equal. I'm going to tell you that the way to think about this is that this is the first rectangle, second rectangle, third rectangle, and that's what I'm saying down here with the k. So I think you would agree, if you understand what a left Riemann sum looks like, is that we want to, for the area of this first rectangle, we want to do f of a. Then the area of the second rectangle, we want to do f of x sub 1. For the third one, we want to do f of x sub 2. And so then this is like a computer program and how it gets generated. And so this is the statement that they're making, that this represents the left Riemann sum. Okay, well, so what the heck does that mean? Okay, so again, so what we're saying is I want the height of the first rectangle. So, and again, this is like a computer program. So the computer is going to start at A. Okay, my thing's off here, my picture's off. So it's going to start at A, and then if we plug in 1 into this formula, that'll be a 0. So then it's saying we're starting at A, and then I'm adding no more changes in x's. Okay, so I'm starting at A, I'm not gonna add anything else, I'm just gonna use this x value. And that's how we're plugging that in. Okay, and so then we move to the second rectangle. Okay, again, the computer or the summation is gonna start at A, we plug in 2 now, this value becomes 1, 2 minus 1 is 1, and so then we're gonna add 1 change of x to our initial value A. Wherever we started, we're just gonna add 1 more. Right? So we start here, the computer starts here, calculates 1 change of x, that gets us here, so then we're gonna plug in f of x sub 1. And that's how we get that height. Right? And again, the same thing. On the third rectangle, we're starting back at A, 3 minus 1 is 2, so then to that x value A, we're going to add 2 changes of x's. Start at A, add 1 change, 2 changes of x, that gets us x sub 2. Right, you can think of it here. Oops, you can think of it here as well. We start at A, we add no changes of x, f of A. We start at A, we add 1 change of x. That's x sub 1. We start at A, we add 2 changes of x. 1, right, 1, 2, and that would generate x sub 2. So that's what they're doing with that. That's why that works for the left Riemann sum. So then let's look at, hopefully I can get it all on. Yes, good. So like here is a right Riemann sum. Okay, notice that the grid points are the same, or they look the same, right? This is representing the first rectangle, second rectangle, third rectangle. But now they're saying instead of the case k minus 1, it's just k. Okay, so again, we need to have the computer or the sigma notation generate these values for us so that we don't have to hand do every single one. So again, we're going to start at A, right? We want, on the right Riemann sum, we want to evaluate f of x sub 1 for this first one. So how does that work with this? Well, when we plug in 1, right, then this is going to be 1 change in x. So we start at A, and we do 1 change in x. And that generates f of x sub 1, right? Next example, if we start at A, plug in 2 into this equation, or this statement, then we are starting at A and then adding 2 more changes of x, start at A, 1 change of x, 2 changes of x, that's the value we're gonna evaluate our function at, right? On the third rectangle, again, we're starting at A, and then we add 3 changes of x. Start at A, 1 change of x, 2 changes of x, 3 changes of x. That is the correct x value to evaluate our function at. And so then we would have got the correct heights. Okay? So remember that it's also going to take this, if you don't change it, like if you don't factor out a change in x, then you're going to, you're actually multiplying it every single time. Okay, and the notation will take care of that as well. It's like we can factor out that change in x if we want. Okay, but as is here, it's doing it every single time. Getting a y value, multiplying it by our change in x, area of rectangle 1. Getting a different y value, multiplying it by our change of x, right, area of rectangle 2, etc. Okay, and so then here's the final one that we would have. It's the midpoint Riemann sum. Okay, and so And, instead of evaluating at the endpoints, we have to evaluate the function halfway in between these, right? The same grid points, still representing the first, second, and third rectangle. But you see what we're doing here is dealing with the midpoint, and that's where the half is. And remember, it would be halfway down. And so then how does this work? So if we want to find the height of the first rectangle, we're still starting at A, right? Plug in 1 here, you're left with a half. And so then we're going to start at A and go half of a change of X. Start at A, half of the change of X, that would produce the correct height, right? On our second rectangle, start at A, move down the X-axis, 1.5 changes of X. 1.5 changes of X. Right, and then the third one is the same way. We start at A and move down 2.5 changes of X. 1, 2.5, that's generating the correct Y value for us. So that's what's going on with that notation. And I'm not saying that just watching me talk through it is gonna get you all the way there, okay? It's gonna be a little bit of re-looking at it before it really kind of clicks. The other thing that we want to make sure we understand is if our function is increasing, a left Riemann sum will be an underestimate, a right Riemann sum will be an overestimate, and so then the midpoint is going to be the most accurate. If the function is decreasing, these statements were opposite, and the midpoint Riemann sum will generate the most accurate estimate. In the long run, it's not going to make any difference to us if we're going to think of left, right, and midpoint, because remember, we're shrinking up this change of X so small that it's not going to make any difference. So for the most part, I think you should be using the calculator, and I didn't bring a calculator, so I don't have anything that I can type it in with you, but I think you're just going to use the calculator, and I need to point something out so you understand what you're trying to type in. So this is down at example 5, and the function that we're talking about is x cubed plus 1. It's worth typing all this, graphing all this stuff so that you can actually see what you're looking at, okay? We're going on a pretty small interval, but we're subdividing it into 50, okay? So again, this is why we want sigma notation. We don't want to do 50 areas and add them up, okay? We still need to generate our change in X, and it's done the same way. And so this is a very small change of X, okay? And so then x cubed plus 1 is what we're talking about. So when you go to your calculator, basically all you're doing is typing it in. And I'm sorry I can't find it. It's under the calc option. Sorry about my shakiness here. Okay? But what they're saying, okay, is let's do the left, okay? And this is just the left one. The one we just talked about. Notice we're starting at 0 because that was our A. Our change in X is what we found. And so then we're just plugging this K in. This K, if you're understanding, is letting the sigma notation know which value to start out. Which rectangle are we talking about? Okay, they simplify this. And then they just make this statement where they're saying, okay, we're evaluating, because remember, X sub k star, right, is what's generating by, the thing I just showed you guys. All right, and then they just say, okay, so we're going to make 50 rectangles. We're evaluating our function this way, right? We got that there. That's at x sub star. That's what we're plugging into our function. And then we're multiplying it by the change in X. That generates our area. Okay, and so it adds up 50, and they just go straight to here. But unless, and I don't know, and maybe you guys can figure it out, but unless you can put in the function somewhere, you actually have to evaluate that out when you type it in. And so what I mean by that is, remember we're talking about x cubed plus 1. And so they do this down here at the alternative solution. Okay, so then, right, we're doing this for x, so they switch to the right Riemann sum down here. Yeah, so the right Riemann sum. So the formula is slightly different. this was for the left. Here's the right. Okay, so they did it the same way, right? They started at 0. They're not working this one out like they did this one, right? They're starting at 0, and then the change of x is still 0.04, and so 0 plus 0.04k is just 0.04k. And so they say, okay, we're going to evaluate this function at 0.04k because that gives us, sorry about this, that gives us the right Riemann sum. Sorry. Okay. So again, you have to type it in as x cubed plus 1. But the x, instead of just saying x cubed, you're going to say 0.04k cubed. And that's what they're doing down here. Where is it? Right? X cubed, what are we plugging in for x? Well, this thing that we just found. This is our x star sub k. Cubed plus 1. That generates the exact height for our 50 different rectangles multiplied by the width. Okay, and so you do have to put it in, unless you can figure out how to put in a different way. Okay, so that should get you guys going pretty good. I do expect some questions, but 43 through 45, 43 and 45 are basically just what that example 5 is talking about. You should do it on the calculator. Okay, don't try to do this. You can, if you want, play around with the sigma notation thing, but I think as of right now, just getting it all the notation in the right order is pretty important. We will talk about 47. I do want you to try 49 and 51. If you really know what you're doing, you'll be able to figure that out, but it is a little tricky on answering this, and if you're a little off, it'll be very confusing, and you'll probably look at the answers and say, okay, fine, but you might not feel real comfortable, so we can talk about those. You should be able to do, definitely you want to look at 55, definitely 53, right? Definitely, it's not focusing. Definitely work all the way up to, like, is not focusing. Try to get to 61 anyway, okay? And we'll see where we're at. The other thing you guys probably ought to do is that progress check, get that thing straightened out that I gave you from before. Good luck.